until its north pole is opposite the south pole of the stator. The direction of the armature's current is then reversed by a device called a commutator, changing its north pole to a south pole. The two south poles repel each other, pushing the armature forward. The current reverses every half turn, keeping the armature in motion by frustrating its effort to bring north poles near south poles. Magnet-driven motors and generators accelerated the 20th century's modernization through electricity. Two inextricably linked industries powered one another's advancement.
The rise of the electrical industry involved a great growth in the use of magnets, and also these things work together. As the industry grew, magnets got better. As magnets got better, the industry grew. So it was very much a symbiotic relationship between magnets and electricity.
Experts advanced both industries by developing new generations of magnets with ever-improving properties. The first commercial magnets were made from carbon steel, and later tungsten steel. These were stronger than the naturally occurring lodestone, but heat and jarring could significantly reduce their magnetism. In the 1930s, researchers created a stronger, more heat-resistant variety called Alnico, an iron-based alloy containing aluminum, nickel, and cobalt. Still widely produced today, they stored greater magnetism in a smaller package. But without an electric jolt, their magnetic potential remained dormant.
You need a very large magnetic field to magnetize them adequately. So what you want to do is have an electromagnet with a large current.
Magnetizing the material is a swift and simple process. Just place the wannabe magnets close to an electromagnet, then turn on the juice. The intense magnetic field realigns the alloy's atoms to make it magnetic. In the 1950s, Alnico magnets were joined by low-cost compact alternatives called ferrites. Today, these iron oxide compounds account for about 90% of the permanent magnet market.
The ferrite magnets allowed motors to be made in a smaller diameter, shorter length, and really the application fitted itself very well for the automobile industry. Now you could have seat positioner motors, for example, that fit very nicely beneath the passenger seat, and window lift motors that were now small enough to fit very nicely into the door of an automobile.
Today, magnets play a key role in not only our cars, but also our computers. Researchers exploring new frontiers in that field are beginning to see the light. The most powerful known magnetic object in the universe is a neutron star, SGR 180620, in the constellation of Sagittarius. Its magnetic field is 1,000 trillion times stronger than Earth's. Magnets will return on Modern Marvels. We now return to magnets on Modern Marvels. No device illustrates the march of miniaturization and advances in magnets better than the cell phone. When retailers unveiled the first generation of models in the 1980s, they were as big as bricks and just about as heavy. Over the years, smaller and smaller transistors helped designers create phones with footprints no bigger than a business card. But without a tiny rare earth magnet for its speaker, a model this petite would never have been possible. Rare earth magnets were first developed in the 1970s and 80s, derived from a group of scarce metals that until that time were very difficult to refine.
They've found that adding these metals to samarium and cobalt together make a very powerful permanent magnet. These are extremely strong. If you take a magnet made of samarium cobalt, just 3/8 of an inch square, and you bring them together, you physically have to work very hard to pull them apart.
The mighty and minuscule rare earth magnets have helped power the age of mobile computing. They're an integral part of every laptop's miniature disk drive. The relationship between magnets and computers dates back to the 1950s, when scientists explored the idea of using magnets as repositories for information.
A North Pole up gives one measure of something. A North Pole down gives another measure of things. And once we can say, this is yes and this is no, then we can build a memory device out of it.
Most computers today come equipped with hard drives featuring a layer embedded with tiny magnets. The north-south configurations of those magnets contain encoded information.
The hard drive is magnetic. There's a read-write head in the computer that rides just above this rotating disk, and as it rotates, it writes and reads little bits and bytes of information on that disk. It could be a south pole, and next to it, it might write a north pole, so you'd have a 1 and a 0.
Ones and zeros are the components of the so-called binary language of computers. What would appear to us as an ocean of indecipherable numbers contains data easily digestible by the computer's processor. Magnetic hard drives, however, retain only part of a computer's data. Semiconductors provide its primary memory, in which most of the computing takes place. The semiconductor memory, known as RAM, is faster, but carries a distinct disadvantage. When you shut off the power, the data disappear. Rebooting your computer takes several minutes because it's reloading the lost data onto the memory chips. Researchers, including MIT professor Carolyn Ross, are searching for an alternative, using magnets.
The next big thing that's coming along is called MRAM, that's Magnetic Random Access Memory, and what that is a magnetic chip that you can put in your computer, and it acts like the memory chips we have now, except that when you turn the computer off, the information stays there, and so when you turn the computer back on, all the information is still there and the computer comes on immediately without having to wait for it to boot up.
To determine which magnetic material might make the best MRAM chip, researchers place samples in a machine called an alternating gradient magnetometer.
This machine has a couple of big magnets. These are electromagnets. So we pass a big current through some coils, and that produces a magnetic field. And it characterizes the magnetic properties of a material, so we can assess whether that will be a good material to use in an MRAM or a hard disk, or other applications like transformer cores, which all use magnetic materials.
As the quest for MRAM continues, researchers at Ohio State University are exploring an intriguing alternative. They've created an unusual magnet that also promises to start your computer in a flash. It's made not of iron or steel, but plastic.
Presently, plastic magnets remain sensitive to the air. So in our research and our development, we keep our plastic magnets in environments which have no oxygen and no moisture.
Researchers produce the plastic magnets by mixing two chemicals, vanadium hexacarbonyl and tetracyanoethylene.
What I have here is the vanadium TCMe that's been deposited on a piece of Teflon tape. The easiest way to tell if it's magnetic or not is to stick it next to a magnet and see if it attracts.